right, y'all. So today we are starting our lesson in Calculus 1. And I enjoy calculus. I don't know if you guys enjoy math or not. If you're here, it's probably because you've taken a lot of math already, right? You probably want to be an engineer or computer, something with computers or something like that. But calculus is a very interesting subject matter. Calculus is the mathematics of change. That's what calculus is. It's the mathematics of change. Now, in pre-calculus, you learn different topics. And when I teach pre-calculus, I always talk about, you need to know this for calculus. You need to know this for calculus. Because I do. I love calculus. Um, and there are some things that kind of filter over from pre-calculus algebra to calculus that you would see at a different level than you saw in pre-calculus. But calculus is pretty much the mathematics of change. There are two major problems in calculus, two major kind of issues. One is called the tangent line problem. Okay? Pretty much if you have a graph, and this is a curve, you have a point P, and a tangent line is where you draw a line going through that point that only touches that graph in that one place. That's a tangent line. And we're just going to talk about what that is. We're not going to get deep into it today. We will get deep enough into it later on. But that's one of the major topics. So the tangent line problem is going to lead us into the first major topic that we're going to discuss in in calculus, and that's going to be differentiation, taking a derivative. How many of you have had calculus before? Maybe in high school somewhere. You've seen it a little bit. Okay. So this problem leads you into that major discussion of differentiation. Um, a secant line where you may have a line going through 2 points. You move this line, or this point keeps moving on down until where you only cross that particular point at one place. Okay? So that secant line keeps on going and it becomes a tangent line. And I said we will definitely get more and more and more into that. The second thing that we're going to discuss is the area problem. And that's the area underneath a curve. The area underneath the curve. How do we find the area underneath the curve? Well, if you see this pink portion here, does it look pink to y'all from back there? No, it doesn't, does it? It looks pink here. Ooh. Okay, basically, you want to find this area that I've highlighted here under this curve. How do we do that? Well, we can draw inscribed or circumscribed rectangles in here of a uniform width. And what we can do is find the area of each one of these rectangles and add it up. Now, doing that will not give us an exact area because there's going to be what? Some space that we don't account for, right? But it gives us a pretty good approximation. This topic here is going to lead us into integration, and that's the second major topic in Calculus 1, okay? So those are just two major things. This is all we're going to talk about in 1.1. There will be no homework in 1.1 for you to do. Just basically introducing the two major things that we're going to be kind of just going to spur off these topics in Calculus 1, okay? So let's get into the meat of something today. We just talked about that stuff. In 1.2, we're going to talk about limits. Limits. What is that? What is a limit? Um, and how do we find these limits? And what is all this? Well, those two major topics that we just talked about, the tangent line problem and find the area underneath a curve. And we said, hey, that tangent line problem is going to lead us to the topic of finding a derivative. that find the area under curve is going to lead us to integration. Both of those major topics are first introduced by the concept of a limit. Okay? So let's kind of look at something and we can kind of conclude what a limit is. If we look at this function, f of x equals x minus 2 over x squared minus 4. Let's just explore this function for a little bit. If I put x equals 2 into this function, then I will get something that has a 0 in the denominator, therefore it's undefined. Okay? But let's look at some numbers around 2. So let's look at the behavior of this function near x equals 2. And let's look out on either side of that. So we're going to get some x values. And then we're going to find the associated f of x value. So suppose I look at 1.9. I look at 1.99. I look at 1.999. Those are values very close to 2, isn't it? So I know that 2 is undefined. Well, let's say I look at 2.001. I look at 2.01. And I look at 2.1. Okay? Suppose I look at those values. And I take this 1.9 and I put into this function wherever there's an x and I simplify. And if I do that, I'm going to get 2.564 or 0.2564. If I put in 1.99, you don't have to do this, but if I put in 1.99 for x here, for x there, and I simplify, I get 0.2506. And if I put in 1.999, 0.2501. We know putting 2 in there gets us something undefined. We don't get a value. But if I put 2.001, I get 0.2499. If I put 2.01, I get 0.2494. If I put 2.1, I get 0.243. So if I look at numbers around this 2, as I am coming in from this way, I'm coming in, looking at 2, looking at numbers bigger than 2. I'm coming in from the right. These function values, 0.243, 0.2494, 0.2499, that's very close to 0.25, isn't it? As I'm coming in from the left, I have 0.2564, 0.2506, 0.2501. I'm getting close again to 0.25. So the function values they get closer and closer to 0.25. This, y'all have to excuse me, I've been under the weather. This is an estimate of the limit. That's an estimate of the limit. That's an estimate of the limit as x approaches 2 of x minus 2 over x squared minus 4. That's an estimate for this. So one thing we notice is that if you find the limit means you're going toward a particular number. Okay, the limit as x approaches 2. So as we're going toward 2 on either side, we should be going toward the same value on either side. And we're going to get to that. It's going to all be in a theorem in a minute. Okay? Now notice that this function itself, it does not exist at 2. It's undefined. But approaching 2, there isn't a limit. So what does this mean? Or did I go all the way there? Okay. So what does this mean? So common types of behavior associated with non-existence of a limit. Now we've already said, no, this is math 125. It should be one of those right there. Okay. Okay. All right. So, okay. So we just said, hey, we're approaching 0.25 from both sides. That limit will exist. But what happens if the limit does not exist? Number one, f of x will approach a different number from the left as it does the right. So before, if we were approaching the same number, 0.25. But if you approach a different number from the left that you do from the right, the limit doesn't exist. Number two, f of x increases or decreases without bound as x approaches c. So we know that when we talk about f of x increasing or decreasing without bound from pre-calculus, that means that we may have a vertical asymptote somewhere, right? Where that graph is going toward it, but never touch it, keeps on going up, keeps on going down. Okay? So you may have somewhere the vertical asymptote. Number three, f of x oscillates between two fixed values. So you may get negative 1, 1, negative 1, 1. You know, it's still not going toward the same value. So we're going to look at some situations where the limit does not exist before we get into the limit existing, okay? What I do when I'm lecturing, pretty much, for the most part, I don't do examples in the actual text unless they're very important. Most of the times, I do even number problems. Now, my notes, you may see problem numbers here that don't match up to problem numbers here because these notes are probably done on the 7th edition of the textbook. Like I say, I just told y'all, 7th, 8th, 9th, 10th, 11th, 12th, it's all calculus. You know, it really is. And for the most part, you may not even use your book a whole lot, okay? So just know that the number may not be the same, but the problem applies. Okay, problem applies. So as I said, this is an example, and it may not be example 3 in the book, but I rarely do these type in the book unless it's a classic example that we need to discuss. All right, so here we want to show that this limit does not exist. We have the limit as x approaches 0 of the absolute value of x over x. Now, one thing that we haven't discussed is how, and right now we're looking at behavior around this limit, but one thing that we can do, if you can do it, is direct substitution. Actually put 0 in there. If you put 0 in there, you get something that's undefined. Now, we've already seen that the first example that we did today, we put 2 in there. It was undefined, but that limit existed, didn't it? So that doesn't mean anything. So what we may need to do is to look for numbers around 0, like we did before. So let's look at numbers. I should say x values around 0. So let's look at x, f of x. Let's put in -3, -2, -1, 0, 1, 2, 3. So if I put -3 into this function, the absolute value of -3 is what? 3. And 3 divided by -3 is what? -1. If I put -2 here, the absolute value of -2 is +2. 2 divided by -2 is what? -1. The absolute value of -1 is 1. Divided by -1 is what? -1. Let's go on the other side. Absolute value of 1 is 1. Divided by 1 is what? 1. Absolute value of 2 is 2. Divided by 2 is 1. So even for 3, we're going to get 1. So on the left-hand side, we have -1 going in. On the right-hand side, we have 1. So this limit does not exist, and it's for reason number 1 here. We are approaching a different number on the right and the left. Okay? So we already know it didn't exist. It told us that. It told us to show that it didn't. And we have to be approaching what? The same. Okay? Questions about that one? Excuse me. All right, so next we have the limit as x approaches 0 of 1 over x. Direct substitution, if I put 0 in there, I get something that's undefined. And this is, again, this is not going to exist. We're looking at things right now that won't exist. So if f of x equals 1 over x, what does that graph look like? Anybody remember? In pre-cal algebra, we had some common graphs that we needed to know the shape of them. This is the graph of f of x equals 1 over x. It has a vertical asymptote at x equals 0. It has a horizontal asymptote at y equals 0, which means coming in from the right, this as we approach 0 from the right, this graph does what? Increase without bound. As we come in towards 0 from the left, this thing does what? Decreases without bound. So this does not exist because the limit as x approaches 0, and we're going to get into notation, and I hate the way they do this. They talk about this now, but they really don't get into the notation until you get in the next section, but we're going to talk about notation now. The limit as x approaches 0 from the left. When you have a superscript over that 0, that's a negative sign. This is that you are approaching 0 from the left. So the limit of f of x, the limit of 1 over x as x approaches 0 from the left, you're coming in. So this line is going toward what? Negative infinity. And what this means is that it decreases without bound. And then you have the limit as x approaches 0 from the right. So now if you have a superscript of a plus sign, so the limit as x approaches 0 from the right, coming in from the right, this thing goes to what? Infinity. So we increase without bound. So y'all, this is situation number 2. Okay? We've done situation number 1, situation number 2. So this does not exist because decreasing and or increasing without bound as you're going toward that 0. Okay, y'all. I know some of y'all may be lost. We're gonna find you. It's gonna pan out. Don't panic first day. I know this is stuff that you've never seen before. Most of you, if you've never seen calculus, it we will cover some theoretical things, and then we'll get into some more analytical things that you can actually sit and do problems. Okay, so just hang with it for a little while. Okay. Any questions about anything so far? All right. Our next problem is oscillating behavior. Remember, we had 3 things of the non-existence of a limit. You approach a different number from the right as you do from the left. You increase or decrease without bound, or you oscillate. Now, we have the limit as x approaches 0 of sine 1 over x here. And I cannot draw worth a flip, y'all. I cannot. But if you do have your textbook on page 51, there is a picture of this. I should have put it here, but I guess I did not. And I see most of you probably don't have a text. But we're going to do, again, we're going to look at behavior around 0. So we're going to look at some values that are convenient to us. 2 over pi, 2 over 3 pi. And we're doing that because really 1 over x, 2 over pi will be like what? Pi over 2. Okay? We're going to look at 2 over 5 pi. We're going to look at 2 over 7 pi. So we're just going to look at values, 2 over 9 pi and 2 over 11 pi. Okay? And here again, with trig, some of these values are coterminal to some coterminal, y'all. That's a thing from trig. See, some of these values are coterminal to other values that we know. But if we put these values into sine of 1 over x, you're going to get 1, negative 1, 1, negative 1, 1, negative 1. And the graph of this thing is going to look something, starts like sine, and then it starts doing this right here. It does. You have a book. That's what it does, doesn't it? It does. It does that. It flip-flops back and forth. So I told y'all I can't draw, but hey. But it does flip-flop like that. I'm not exaggerating. So it goes from 1 to negative 1, 1 to negative 1. So it does not exist because we're doing what? We're oscillating. Okay? So, but all that's good and fine. We talk about the non-existence. What about the existence of a limit? What about the existence of one? We don't want to, most of the things are going to be find the limit if it exists, not show that it doesn't exist. You may have some, but sometimes it's good to see the other half of that. You know what happens when it doesn't exist. So let's get into what this limit is. We're going to look at it informally, before we go and get the formal theorem for what it is. I need y'all to open up your minds. All right. We're going to look at the informal definition first. If f of x becomes arbitrarily close to L as x approaches C from either side, then the limit as x approaches C of f of x is L. Now let's break this down. F of x becomes arbitrarily close to L as x approaches C. Now what in the world does that mean? Arbitrarily close to L. So the limit as x approaches C of f of x. If you look at values around C, this is C. If you look at values around C, then you may get some function values. Let's think about this as x and y axis. You may get some function values, let's say here, there. They just may be sporadic. But as you get closer and closer and closer to C, then these function values should be getting closer and closer and closer to L. So in the beginning, they may be sporadic. They may be all over that line. But at some point, when you're getting very close to C, then these function values, if L is the limit, should be getting close to L. Now, what does this word close mean? Well, once we get to where we're picking these C values that are getting, picking the values close to C and we're getting close to L, then we have become in a delta interval around this C. This here is the lowercase Greek letter delta, okay? So somewhere we are in this interval, C minus delta, C plus delta, where when we start picking these C's, we're getting closer and closer and closer to L. Now, as we're getting closer and closer to L, then there is an epsilon distance around L, okay, too. L minus epsilon, L plus epsilon. So as C, as we honing in on C, we're honing in on L. So there is a epsilon distance, a very, very small distance around C and a very small distance around L. And there's going to be a point where we're going to reach that delta distance around C that's going to point toward L. Now, that may sound confusing, but this informal definition is going to lead to the formal definition of what a limit is. So, we let epsilon, Greek letter epsilon, represent a small positive number then f of x becomes arbitrarily close to L means that f of x is in get to writing fast. This thing jumps. Gets in the f of x is in the interval. L minus epsilon, L plus epsilon. Or the absolute value of f of x minus L is less than epsilon. Epsilon is a very, very small positive number. So, f of x becomes arbitrarily close to L. That's what it means. These values are getting into that epsilon distance around L. Okay? Now, we had this what? X approaches C. What does x approaches C mean? This is what it means for f of x to be arbitrarily close to L. What does it mean for x to approach C? We're going somewhere, y'all. Take the journey. This means there exists a positive number delta such that x lies in either interval C minus delta, C minus delta, comma, C, or C, comma, C plus delta. And if it lies in one of those intervals, what that means for us is that the absolute value of x minus C is less than delta. We didn't have to put that 0 there because absolute value implies what? It's bigger than 0. That the absolute value of C is less than delta. So what this means is that x is within delta distance of C. And I know right now you're saying, I don't understand anything Dr. Bergen's saying. We're getting there. Take the ride. Stay on the journey. All right, so we said f of x becomes arbitrarily close to L, means that there's some epsilon distance around L that we're getting closer and closer to L. What that means is that we have gotten closer and closer to C, and there's some delta distance around C. And what does all this have to do with anything that we're talking about today? Well, let's get to this formal definition of a limit. This is the formal definition. Let f of x be a function defined on an open interval containing C, except possibly at C. Because the very first example we had, the function itself did not exist at 2, did it? But it had a limit. So it does not have to be defined at the actual C. Okay? So, and let L be a real number. The statement that the limit as x approaches C of f of x equals L means that for every epsilon greater than 0 that you pick, or that's out there, there exists a delta greater than 0 such that if this absolute value of x minus C is less than delta, then the absolute value of f of x minus L is less than epsilon. Yeah, so what does that mean? That means that for a given epsilon, and in the first couple of problems that we're about to do, they're going to give us an epsilon. For a given epsilon, you should be able to find delta after you do some calculations, some little algebra. You should be able to find a delta, that delta to where there is that distance that around C that we're going to start honing in toward that limit L. The goal here in these problems that we're about to do is to find that delta, to find what delta is. Best way to do it, let's do some problems. Now we're getting into doing something. Haven't done a whole lot today. We've talked a lot, but you got to know the backstory. You got to know what this stuff means. So, in exercises 39 through 42, find the limit L. And that may happen by what? Direct substitution, if we can do that. It says then, they want us to prove that the limit is L. They say find the limit L. Sure, we find it. We know what it is. But we want to prove that it's L. And to prove that it is indeed the limit, then we need to find a delta such that the absolute value of f of x minus L is less than epsilon. Here, we are given an epsilon. Not every problem will you be given epsilon. Sometimes you're just going to be saying, hey, just epsilon greater than 0. Here, the epsilon they're giving us is 0.01. So they want us to find delta such that the absolute value of f of x minus L is less than that 0.01 whenever this absolute value of x minus c is less than delta. So what does this mean? First of all, we're going to start off with the absolute value of f of x minus L is less than epsilon. And then we're going to do some work, a lot of stuff. Do some work may encompass a lot. But we're going to do some work until the left-hand side of this thing here looks like the absolute value of x minus c. Okay? And over here will be some number, and that's going to be your delta. So in other words, to start this problem, what is L? What is L? If I put, here we're looking at the limit as x approaches 4 of 4 minus x over 2. So this is 4 minus 4 over 2, which is what? 2. This is L. Okay? Direct substitution. So we know what the limit is. Now we're going to prove that it's 2 by this epsilon delta definition. So I need to start off with the absolute value of f of x minus L being less than epsilon. So what is my f of x in this problem? What is it? 4 minus x over 2. What is my L? What's my epsilon? Okay, so I start off with this. In the back of my head, I need, what is my goal? What am I trying to get to? We're going to have to do work on this until we get to absolute value of x minus c. What is c in this problem? The limit as x approaches c. X approaches what here? So I need to work with this left-hand side until I get to the absolute value of x minus 4. Okay? So you start off with the absolute value of f of x minus L is less than epsilon. You work that left-hand side until you get the absolute value of x minus c. Well, we need to have a mental note of what x minus c is. So that's our goal. We need an x minus 4 over here. Well, how do I get x minus 4? I guess this thing cuts off after an hour. That's gonna suck. Okay. All right. So I need to work with this until I get the absolute value of x minus 4. Well, let's see what we have going on here. Over here, we have what? 4 minus 2 is what? 2. Right? I just combined my constants. That's all I've done. And I need x. What can I factor out so that I have plain old x right here? Not 2, but negative what? Negative 1/2, right? So if I factor a negative 1/2 out, I'm going to have x here. So if I factor a negative 1/2 out from this 2, I know my sign is going to change. And this ends up being what? 4. Because negative 1/2 times negative 4 is what? It is positive 2. So remember, there's a little property that says the absolute value of A times B is the absolute value of A times the absolute value of what? B. Y'all remember that property? Then the absolute value of negative 1/2 is what? Positive 1/2. Well, I can definitely get this on this over here by itself. Now, if I multiply both sides by 2, I have the absolute value of x minus 4. Then I do 2 times 0.01, which is 0.02. So what I have done is I've started with the absolute value of f of x minus L on the left-hand side. I've gotten to my goal of the absolute value of x minus 4, which means that my delta is 0.02. Remember I told y'all the goal was to find that delta that makes everything fall into place. That delta is 0.02. So we have proved that 2 is the limit by finding, or verified versus basically, that 0.02 is delta. Okay? Now, in this problem, notice that it worked out so good, didn't it? It did. We could factor out that negative 1/2. You know, negative 1/2 is a constant, and we were all good. But we know it's going to get harder. So now we're going to do one that's not so good. It's not going to work out that way. Any questions about this before we go and look at where we may have a little issue going on? All right. Here we go. We're going to have a little issue with this one, but that's okay, because we're going to handle the issue. We're looking at the limit as x approaches 5 of x squared plus 4. The directions are still the same here. We're still using epsilon being 0.01, okay? Still using that in this particular problem, okay? So, what's our goal? We need to keep that in our head. The absolute value of x minus c. What is c in this problem? What is it? 5. So we need to have in our head, my last step, I need to have an absolute value of x minus 5. Okay? But how do I start? First of all, I need to find the limit. What is this limit? Direct substitution will give me what? 5 squared is, plus 4 is 29. So y'all, that's my limit. That's my L. So I need to look at the absolute value of f of x minus L is less than my epsilon. So my f of x here is x squared plus 4 minus my limit of 29 is less, and they gave me an epsilon of 0.01. And I need to work with this until I get absolute value of x minus 5 on that left-hand side by itself. But we've already said it's not going to be as straightforward as the last problem. So over here, I can combine. I get x squared minus what? 25. And y'all, I can factor this to be x plus 5 times what? X minus 5. And I can go ahead and put those in their own individual absolute value symbols. So I do get the absolute value of x minus 5 being less than 0.01 divided by the absolute value of x plus 5. Delta is a constant. Okay? So we got this absolute value of x plus 5 in that denominator down there. But y'all, delta needs to be a constant. It's a constant bigger than 0. So how are we going to find what that is? So let's talk about that. So y'all, this is not a constant. So what we're going to do is to look at an interval around RC. And remember here, C is 5. Okay? And we're going to look at C, or this X being around, or this interval around 5 being 4 and 6. That's an interval around 5, isn't it? And what we're going to do is we're going to look at x equals 4, and we're going to look at x equals 6, and we're going to find a value that makes that the value that makes that right-hand side the smallest. And that's what we're going to pick to be our delta. So 0.01 divided by what? Absolute value of 9. That's about 0.0009. And then we're going to look at 0.01 divided by the absolute value of 11. I don't have that value, but I would assume it's 0.011 maybe. Probably. So which is the smaller value? This is the smaller value. So we're going to pick that smaller value. And we're going to call delta 0.0009. So what if I had picked, I don't know, some other value? It's best to pick integers that make your calculations convenient. So we're going to do another one where we may not pick the absolute next value. Okay? So in this situation, you know what? Your answer may be different than the person next to you. You know, maybe. But you want to pick the smaller of that. So pick an interval. When you get this situation where you found that x minus c, but over here you got some stuff that's not a constant, pick an interval around c and get the smaller value. Okay? Questions? Y'all ready for another one? tired? It's okay. We got a little more time. We're here to 10:40. Yes. Because you want delta to be as small as possible. Because you want that interval to be so tight that you make sure you've gotten into that space where you need to be where we're getting toward L. Other questions? All right, let's look at a few more. We don't have that much longer to go. And we're actually doing problems now. Okay. So now we look at the limit as x approaches 2 of -1. Well, guess what? There's no variable here to put in there, but the limit of a constant is that constant. Okay? The limit of a constant is that constant. So, let's look at the absolute value of f of x minus L. Again, our epsilon. Okay, we have some different directions here. Here, we're just going to let epsilon be bigger than 0. So here we have gone, you have to read your directions carefully, and I didn't put them there. Okay. What the directions say is that to find the limit L, let's go back and let me write the actual directions. And the directions I'm about to write are going to be for the rest of the problems that we're going to do today. Find the limit L. Then use the epsilon delta definition to prove the limit is L. So in this situation, in these directions, they did not give us a specific epsilon. So you just let epsilon be bigger than 0. So we've already said that limit is L. So our f of x minus L less than epsilon. So the absolute value, our f of x is what? -1. Our L is what? -1 less than epsilon. So what do we have? We have -1, double negatives make positive. So we have the absolute value of 0. 0 is less than epsilon, which I like to see the other way. That means epsilon is bigger than 0. This can be confusing, but it's really an easier problem. What this means is that on the left-hand side, everything went away. You got epsilon bigger than 0. So what this means is that any delta bigger than 0 will work. Any delta bigger than 0, because here, you didn't get, there is no x minus whatever. There's no x. So here you got, hey, epsilon bigger than 0, any delta will work for this problem. Special problem. They all won't be this way. But any delta bigger than 0, you can pick delta to be what epsilon is if you want to. It works there. Like I said, special problem here because we had no x in there. Well, let's go back to where we have an x. Number 50. And not only do we have an x, we have a what, y'all? A square root of x. So what is this limit? The limit as x approaches 4, the square root of x is what? 2, right? Square root of 4 is 2. So here, the absolute value of f of x minus L less than epsilon. So the square root of x minus 2 is less than epsilon. What's our goal? What do we need to see? X minus what? 4. How am I going to make this look like x minus 4? Any suggestions? Squaring would give us a plus 4, and it'll give us an inner and outer term. You got something else? Almost squaring. Think about it. What did we do when we like rationalized a denominator when you had radicals? What did we multiply by? Y'all remember? The conjugate. So squaring was very good. And I want you guys and ladies, and I'm using guys to be both, okay? I want you to throw those things out there. It helps the thinking process. It helps you think critically. Even if it's not correct, throw it out there. But the conjugate, because what does the conjugate do? When you multiply something by its conjugate, what happens? The inner and outer will cancel. You know, you have a minus b times a plus b, you end up getting a squared minus b squared. So remember that what you do to one side, you must do to the what? Other side. So when we do that conjugate, we have what? X, the inner and outer cancel, minus 4 is less than epsilon times the absolute value, and that should be absolute value, the square root of x plus 2. So y'all, we're in that situation again where on that right-hand side, we just don't have a constant, right? So our C is 4, and we want to look for numbers around 4. And not only are we going to look at numbers around 4, because we know we're taking the square root, let's get the perfect square immediate to the immediate left and the immediate right of 4. So we're going to get the perfect squares. You don't have to, but it makes your work a little bit cleaner. Get the perfect square to the immediate left and right of 4. And what are those two numbers? X equals what? 1, and x equals what? Square is 9, yes. So the perfect square to the left is 1, the one immediately to the right, that perfect square is 9. And so when we do that, if we look at x equals 1, we have the square root of 1 plus 2, which is what? 3. If we look at 9, we have the square root of 9 plus 2, which is what? 5. Which one are we going to use? You want to use whichever one makes this expression smallest. So that's going to be what? 3. So our delta is 3 epsilon. Is it making a little bit more sense? A little bit, maybe? Most times the first section that you get into a chapter, it's going to be a lot of theory, and then you get into the other sections and you get more analytical work. We'll do more analytical work on Thursday. Yes. Okay, we looked for the perfect square that's closest to 4, that's bigger than 4. So what are the perfect squares? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So we were looking for perfect squares. Okay? Other questions? If you have them, please ask. All right, couple of more problems and we're going to be out of here today. 2 more problems to go, or maybe 1. Let's see. Oh, just 1. Last one. Y'all, please don't let me forget to call roll every day. Got to keep up with that. It's on my brain today, but we got to do that. Okay, so now we have the limit as x approaches -3 of x squared plus 3x. What is this limit? So we have -3 squared is 9, and then we have -3 times 3 is -9. So our limit here is 0. And we're trying to get to, what's our goal? We need x minus, absolute value of x minus c. Where c is -3, so x minus a -3 is x plus what? 3. So we got to have an x plus 3 on that left-hand side. So we look at the absolute value of f of x minus L being less than epsilon. F of x is x squared plus 3x. L is what? 0. So that 0 can go away, and I can factor an x out and have x plus 3. Right? So I can call this the absolute value of x times the absolute value of x plus 3 is less than epsilon. So the absolute value of x plus 3 is less than epsilon over the absolute value of x. So you tell me, what are we going to pick? What's our interval? So we need to look at numbers around x equals -3. What interval? Go ahead and say it. Negative what? Absolutely. -4 and -2. So if we look at x equals -4, we have epsilon over negative, the absolute value of -4 is 4. If we look at x equals -2, we're going to have epsilon over the absolute value of -2, which is 2. Which value is smaller? This is the smaller value. Remember, if your bigger number is in the denominator, that really makes it your what? Smaller number. So we have the absolute value of x plus 3 is less than epsilon over 4, which makes our delta epsilon over 4. Okay, so I didn't mention this before, but you do have homework online. There is a temporary access as well. If you have an issue, maybe you don't get paid till Friday or next Friday or whatever that may be, I think they give you 14 days free access, so you can start doing your homework today. Also, the homework in the online system is not nearly enough practice. So you can go to the end of the section and do some of those odd number problems that you have the answers to for more practice. You need to do as much practice as you feel you need to do until you understand what you're doing. So that part's not graded, but you need to know what you're doing. So it will probably take more than the problems that we have assigned here. For those of you who came in late, read through that syllabus. Go into Blackboard because we're going to be accessing WebAssign through Blackboard. That's very important because when you go to that testing center, they're going to lock down that browser, and that's how they want you to get in, is through Blackboard. Make sure you read, like I said, if you were late, read your syllabus and make sure that you understand. If you have any questions, you can ask me on Thursday. Are there any questions about anything we have covered today in the lecture? Okay. Yes, you don't have any on 1.1.